Okay, we're going to do another word problem, and it's more directly a quadratic word problem. So I'm going to read this aloud, problem's going to go up. Try to copy it or at least highlight the important parts. A rancher wants to build a large rectangular pen split down the middle into two equal-sized rectangles by another fence. They have 240 feet of fencing. What dimensions maximize the area? What is the maximum area? Okay. So hopefully you have a picture in your head of a rancher. Maybe he's riding a horse and he's out somewhere in the West and he's building a rectangular pen for horses, cattle, sheep, what have you. So if we read that, we'll notice that right off the bat, we could draw a rancher, but that doesn't seem mathematically relevant. What we should probably start with is a large rectangular pen. So let's go ahead and let's draw a large rectangular pen. That's rectangular enough for our work. And then it says it's split down the middle into two equal-sized rectangles by another fence. So we're going to split it down the middle, and we're going to notice that this is also two equal-sized rectangles. You know, give my drawing a little space. And it says he has 240 feet of fencing. What does it ask us to do? It asks us to basically maximize the area. Okay, so now we have a picture for what we're trying to do. Let's go ahead and let's start trying to translate this into more of a math problem. So if we look at this, what we want to do is we want to maximize the area. So let's just let A be our area. Okay, now we know that the area somehow is like a length times a width. So we're going to write that down at some point, and we're just going to write that down as a note. Area equal length times width or height or whatever you want to call it. Okay, now this is not in mathematical notation at this stage, but it's holding down something that we need. Now, if we look at this, we might be tempted to say that 240 is what the area should be. But if we think about that, fence doesn't have an area. Fence has a length. You roll it, run it out. So this isn't sort of the right sort of thing. And if you think about it, an area should be like a length squared. So it should be in like feet squared. So this isn't quite the right idea. But if we think about that, if you were going to build a fence, you would build a fence along here, 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 and build a fence along here. So if you're going to do that, you'd like to know how far you have to go. And so we can label those with simple mathematical variables. So what I'm going to do is I'm going to do this by the smaller pen. I'm going to label this length x, and I'm going to label this length y. Now, since these rectangles are supposed to be equal to each other, they should have the same dimension. So it should also be x along the bottom. It should also be y along this side, y along this side, x along this side, and x along this side. So then if you think about that, if we're going to split up that 240 feet of fencing, we need 4 x's and 3 y's. So let's write that down. So we have 240 feet of fencing, and then we add up 4 x's, so that's x plus x plus x plus x, that's exactly 4x, plus y plus y plus y, so that's plus 3y. And so now we have this relationship, and if we look at this, we go back, what's the area? Well, the area is just going to be the length, so that's going to be 2x times the height, which is y. So then if we look at this, we now have two equations that we can use. And when I do this and I have a lot of work sort of about, I tend to box the things I realize are very important. All right, so we can't quite maximize the area yet. That was our goal. And if we look at this, we don't really know how to deal with two variables at this stage. We do know how to deal with one variable when it's a quadratic. And I guess I'll just point this out that there are a lot of more advanced ways to do this. And in fact, calculus gives us a lot of good ways to handle problems like this. But at pre-calculus, we're just using some more basic techniques and getting used to and familiar with these types of problems. So if we notice we have two variables, we need to get rid of a variable in some sense to do that. We can't just erase one of these because that changes the meaning of everything. But this equation gives us a nice relationship between the two variables. So what we're going to do is we're going to solve for one of these variables and we're going to substitute it into the other one. So I'm going to substitute for y here. So if I look at this, that means that 240 minus 4x is equal to 3y. And if I divide by 3, I get y is equal to 240 minus 4x over 3. Okay? So then what I'm going to do is I'm going to substitute that into this equation, and I get a is equal to 2x times 240 minus 4x over 3. Now this is closer to looking like quadratics, but all we need to do is multiply it out. So I'm going to multiply it out and reorder it just so it's a little cleaner to see. So I take the 2x, I'm going to multiply it by the negative 4x first, so that'll give me my 4x squared term. So 2 times negative 4 is negative 8, x times x is x squared, and then that's all divided by 3. And then I also have a 2x times 240. 2 times 240 is going to be 480 divided by 3x. Okay? So next we're going to do is, this is now a quadratic, and just as with the previous problem, this is a downward facing quadratic because this coefficient is negative. So I'm going to just find the vertex, and the vertex is negative b over 2a. In this case, the a is not referring to the capital A area, but it's referring to the coefficient of the x squared. So if we look at this, this is going to be negative 480 over 3 divided by 2 times negative 8 over 3. Now this looks a little scary at first, but that's okay. Notice that they're both divided by 3 in the numerator and denominator. So if we multiply by 3 across, those will cancel. We'll get negative 480 over negative 16. And if you go ahead and calculate this, this is actually going to be 30. So we know that the x needs to be 30. So then we can also solve for the y now using this equation down here. So we get y is equal to 240 minus 4 times 30 over 3. 4 times 30 is 120. So we have 240 minus 120 over 3. And then we have, 120 over 3, which is equal to 40. So these are what we call the dimensions of it. So we need x to equal 30, and we need y to equal 40. And so that gives us the dimensions, and then it asks us to maximize the area. So all we need to do is take our a, which is our area, replace it by 2xy, replace those x and y by the maximum values, 30 and 40. And if we do this correctly, we should get 2,400. And this will be in feet squared, because we noticed that this was 30 feet, and this was 40 feet. So feet times feet is feet squared. So that's the solution to our problem. If we want to tell our rancher what to do, he needs to make these lengths to be 30 feet. He needs to make these lengths 40 feet. And when he's all said and done, he has 2,400 feet squared to put whatever he wants into that pen. And so that's a way to do a problem like this and take advantage of the fact that quadratics have a maximum at their vertex. Now, I want to make one short note if you want to retry this problem, is we don't necessarily need to do the dimensions according to the smaller rectangle. We could go ahead and do it by the longer rectangle. So make this, I don't know, z and make this y. Repeat the whole problem over again, and that different choice of variables will give us the same exact answer. It's just that some of the steps in between will be a little bit different. So if you want to try that now and see if you get the same answer, that would be a good exercise to do before next class.